Okay, I call this the fundamental theorem of calculus. I call this the big kahuna of calculus. Credit goes to Newton and Leibniz for the creation because they actually found the connection between differentiation and integration. And so you can basically read this print here if you want to. But let's go ahead and get on with the fundamental theorem of calculus. Okay, so the fundamental theorem of calculus says if f is continuous on a closed interval from a to b, and f is an antiderivative of little f, any antiderivative, then we can say that the integral, the definite integral from a to b of f of x dx is simply the antiderivative evaluated at b minus the antiderivative evaluated at a. And that's all there is to it. And we do not need to use antiderivatives with constants anymore, because this subtraction up here causes the constants to disappear. Okay? So the constants is 0. Now, you might remember earlier that I asked you to find the area using the fundamental theorem of calculus. And I don't know if we did this one or not, but we did one similar to this where you had to use the definition. Actually, I asked you to do it earlier using the limit definition for integration. Maybe one like this anyway. Okay. Well, you can, if you go back and look at that definition of finding area using that limit definition, you'll see that it requires quite a bit of work. But now let's find the area bounded by the graph of y equals x cubed, the x-axis, from 0 to 2 for this function. Now, before we get into this, you might want to just take a quick look at the graph. Okay, now I just drew a rough sketch here, but remember the function y equals x cubed kind of comes up like this, swings over, and then it continues to increase. It doesn't turn up like I have there, but it continues to increase. Okay, so basically if you look at the graph between 0, which is right here, 0 would be right here, and 2, I drew this vertical line here to represent 2, you can see that we're looking for the area in here, and you'll notice that the graph is non-negative and continuous as we go from 0 to 2. So basically we know that this area can be calculated by this definite integral. Well, now we don't have to use that nasty limit definition anymore. All we have to do is find us an antiderivative of x cubed, which we know with the power rule would be x to the 4th over 4. And so that's going to be our antiderivative, capital F. And then when we do f of b, well, b is the upper limit, so that's just f of 2. So if I evaluate this function at 2, I get 2 to the 4th over 4, which is 16 over 4, which is 4. And then if I evaluate it at a, I get f of 0, which is 0 to the 4th over 4, which is 0. So then f of 2 minus f of 0, capital F of 2 minus capital F of 0, is just 4 minus 0, which is 4. Now, if you want to put a little more compact notation, then this is how we write it. So the integral from 0 to 2 x cubed dx is equal to x to the 4th over 4 from 0 to 2, and then you just evaluate that function at 2 and see what you get, then evaluate it at 0, see what you get, and then take the difference, and you get 4. Hey, that's pretty cool, isn't it? That's a lot better than that other definition. Okay, so basically the guidelines for the fundamental theorem of calculus is, first thing I want to say is, assuming that you can find an antiderivative of the function. Now, some functions, we're not going to experience that here, but some functions will not have an antiderivative, and in Cal 2 you might learn how to approximate those functions using sequences and series. Alright, let's look look at number 2 here. When applying the fundamental theorem of calculus, this is the standard notation. So when you want to integrate from a to b f of x dx, you take the antiderivative, the one without the constant, and then you evaluate that antiderivative at the upper limit, and then evaluate at the lower limit, and then take the difference. And make sure you do it in the right order. It's got to be the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. And I just did this example, so I just copied it down here for you to see. And again, you don't need the constant when doing these because the constants cancel out in the subtraction. So now, let's look at an example. Suppose I want to integrate from 1 to 3 2x. Well, we know how to integrate 2x. 2x would be just 2x squared over 2, which would just be x squared. And we want to evaluate it from 1 to 3. So what I would do is I'd evaluate this function x squared at 3, and then I'd evaluate the function at 1, and then I'd take the difference. 9 minus 1 is 8. Bam! There you go. Alright, what if I want to evaluate the integral sine x dx from 0 to pi over 2? Well, let's find an antiderivative of sine x without the constant. So we know when we integrate sine x, we get minus cosine x. So we're going to evaluate that from 0 to pi over 2. So I'm going to find out what is minus cosine x at pi over 2, and then minus what is minus cosine x at 0. Okay, well, cosine x at pi over 2 is actually, let's see, cosine of 0 is 1, so that would be minus negative. Cosine of pi over 2 is 0, so I'm going to have minus 0. So that's going to just be 0. And then I'm going to have minus a negative 1, because cosine of 0 is 1. So minus negative 1 is plus 1. So I'm going to have 0 plus 1 is 1. Okay, now, what if I want to evaluate this integral, the square root of x from 1 to 4? Well, first thing you got to do is write that so that we can apply the power rule to find the antiderivative that we need. So now, using this function x to the 1/2, if I integrate that, I get x to the 3/2 over 3/2. So I get x to the 3/2 over 3/2. And let's see, I'm not sure. I think this, let me fix this. This looks like a error. Okay, let's back up. I figured out what was wrong here. This is actually supposed to be square root of x over 2. And then when I rewrite it, I can factor the 1/2 out, and I get 1/2. And then I'm going to integrate x to the 1/2 from 1 to 4. So if you integrate x to the 1/2, you get x to the 3/2 over 3/2. Well, you still have the 1/2 here, so 1/2, you're going to have to multiply that by 2/3, because dividing by 3/2 is the same as multiplying by 2/3. Well, 2/3 times 1/2, the 2's cancel, and you just get 1/3. So I just get this function over 3. And then in the next step, I'm going to evaluate this function at 4. So I have 4 to the 3/2 divided by 3. And then minus, using the fundamental theorem of calculus, this same function evaluated at 1. So I have 1 to the 3/2 divided by 3. And so that's actually the square root of 4 cubed. So that's going to be 8/3. And this is the square root of 1 cubed, so that's going to be 1/3. So I have 8/3 minus 1/3, which gives me 7/3. Okay, now let's take a look at this one. Integrating from minus pi over 4 to pi over 4 secant squared x. Well, we know that when we integrate secant squared x, we get tangent x. So I'm going to evaluate tangent x from minus pi over 4 to pi over 4. So I'm going to evaluate the tangent of pi over 4. I don't know why I wrote that twice. I think I did it on the previous example. But anyway, tangent of pi over 4 minus the tangent of minus pi over 4. Well, tangent of pi over 4 is 1. Tangent of minus pi over 4 is negative 1. But we're subtracting these, so 1 minus negative 1 would be 1 plus 1, which is 2. Okay, I got a couple more examples here. Notice this one from 1 to 2, 6x squared minus 5. So you just integrate each term of this. So 6x squared, if I integrate, I get 6x cubed over 3, which is 2x cubed. And then when I integrate minus 5, I get minus 5x. And then I'm evaluating it from 1 to 2. So first of all, evaluate that function at the upper limit, which is 2. So I get 2 times 2 cubed minus 5 times 2. And then evaluate it at the lower limit, which is 1. So I get 2 times 1 cubed minus 5. And then you can do the arithmetic here. 16 minus 10 minus 2 minus 5. So that's 6 minus negative 3, which is 9. Here's another one. You know how to get the integral for x. It's just x squared over 2. Go back to your trig rules and remember that secant x tangent x is simply the derivative of secant x. And so we're going to evaluate this function at pi. So if I plug pi in for x, I get pi squared over 2 minus secant pi. And then if I plug 0 in for x, I get 0 squared over 2 minus secant 0. Okay, well secant pi is negative 1 and secant 0 is positive 1. So I get pi squared minus negative 1, and then over here I get 0 minus 1. So I have pi squared over 2 plus 1 here, and then minus a negative 1 is plus 1, and the exact answer is pi squared over 2 plus 2, because 1 plus 1 is 2. Okay, now if you want to evaluate an absolute value, you really need to think in terms of area of what's going to happen. So let me show you the picture of this absolute value. This absolute value 2x minus 5, to integrate that from 1 to 3, what you're going to find, if you graph that function, you're going to find that right here at 5/2, it changes functions. So you're integrating it from 1 to 3. So we're going from here to here. But here it changes. It has a function with a negative slope as you go from 1 to 5/2. So that would be the minus the quantity, minus the absolute value. Or you could say, you could just flip it around and say, instead of minus 2x plus 5, you could say 5 minus 2x. So from 1 to 5/2, we would actually have to integrate this function. And then from 5/2 to 3, we would have to integrate this function, the other one, which would actually be the 2x minus 5. So anyway, quickly, let's integrate the 5 minus 2x. You get 5x minus x squared from 1 to 5/2. So evaluate this function at 5/2, evaluate it at 1, then subtract the 2, and you should get 9/4. Now, to do the other one, you're gonna integrate from 5/2 to 3, 2x minus 5. So you integrate that, get x squared minus 5x, and then you are integrating from 5/2 to 3. So first we evaluated at 3, then we evaluated at 5/2, and we take the difference, and the difference is going to be 1/4. And now, if we want the answer to the entire integral, it's actually going to be the sum of these two integrals. So absolute value can be a little tricky there, but it's going to be the sum of these two integrals. And of course, you had to switch functions simply because that's what the absolute value does. It actually changes from a function with a negative slope to a function with a positive slope at certain points. So anyway, just add the two integrals together, and that will give you the integral for the absolute value of 2x minus 5 from 1 to 3. And I'll do some more examples on the next video.